In this lecture, I am going to introduce you to Riemann integrals. The simplest way to think about integrals is as a method for calculating areas. We all know how to calculate the area of a rectangle. Well, it's just length into breadth. But how do you calculate areas of irregular figures? For example, how do you calculate the area of a leaf? This is something you may have done in school. You put the leaf on top of a sheet of graph paper. You count the number of squares that are entirely inside the leaf. That would give you a lower bound for the area. And then you could count the number of squares that touch the leaf, and that would give you an upper bound for the area of the leaf. And using finer and finer meshes of squares, you can compute the area of the leaf. Now that's an example of a numerical computation, but there's also some very interesting areas of a geometric nature where interesting things happen. Let me show you the example of the area of a circle. So here's a way to compute the area of a circle of radius r. What you do is you cut the circle up into little wedges as shown in the figure on the left, and then you rearrange these wedges alternating. So the white wedges and the yellow wedges are alternating, and totally the wedges from the left half of the circle are the white ones, the wedges from the right half are the yellow ones. You alternate them and you rearrange them so that they form something that looks approximately like a rectangle. And you can see from this figure that this approximate rectangle has a length pi times r and height r. And so what you get is that the area of the circle is pi r squared. Now this is a very beautiful and clever way of computing the area of a circle, but firstly it depends on this trick of, it only works for a circle. And secondly, there's this little confusing thing as to, okay, it does look almost like a rectangle. Now we know about limits, so we could ask, as we increase the number of wedges that we cut the circle into, if that number goes to infinity, why would this converge to the area of a rectangle? So these are the kinds of issues that we will tackle while talking about the Riemann integral. The idea is very similar to the idea behind computing the area of the circle. We break up our shape into simpler shapes whose area we know and try to use them to approximate the area. So here's the setup. So we have a function f on a closed interval ab which takes real values. So let me just draw a figure. So this is the x-axis, and here's a, here's b, and my function is given by a graph. So something like this, and my objective is to compute the area under the graph. So that is somehow the area between the graph and the x-axis. So this sort of shaded region over here. Not exactly the area, but we are going to think of this as a signed area. So this, any region that occurs below the x-axis would be measured with a negative, and anything that occurs above the x-axis would be measured with a positive. So, so what we want to do is develop a technique to compute this kind of an area, and the resulting area is going to be called the integral from a to b f of x dx. So I'll just call it area under the graph for simplicity, but you need to understand that there's a sign involved. The area that lies below the x-axis comes with a negative sign, and the area that lies above the x-axis comes with a positive sign. Okay, so let's see if we can somehow approximate this area. Can we find lower bounds or upper bounds for this area. So one thing that we could do is just find an upper bound for this area. Well, we could find a rectangle that gives an upper bound for this area. Just take this rectangle over here. So what is the height of this rectangle? Well, it's the largest value of this function on the interval AB. So the height of this rectangle is maximum value of fx, where, or maybe this function that I've drawn here is continuous, so it attains its maximum, but maybe for the general function I should be careful. Supremum of fx, x belongs to AB. Now to make sense of this, we better assume that f is bounded. So the height of this rectangle is supremum of f of x, x belongs to AB. The length of this rectangle, well, it's b minus a. And so what we know is that that this integral is less than or equal to b minus a times this supremum. And on the other side, we can put b minus a times, we can have a lower approximation, so to speak. And this height is, so this is the infimum of f of x, where x belongs to AB. In this picture, this is going to be a negative number. And what we have is that the area lies between but there's a huge gap between this upper bound and this lower bound, right? The gap is b minus a times, in fact, the area of this big orange rectangle that we have in the figure. So the idea is to try to somehow narrow this gap down. And you do this by subdividing this region into smaller vertical strips. So what I'll do is I will, instead of just looking at one rectangle, I'll break it up into several rectangles. They don't even have to be all of the same width. And now let's see if I can somehow refine my lower bound and my upper bound. So what I can do is, for my upper bound, on each part of this interval, I will just take an upper bound. So here what I'll do is I will take this rectangle. Certainly the area of this rectangle is greater than or equal to the area under the curve. On the second segment, I will take this rectangle. On the third segment, I will take this rectangle. On the fourth segment, this. Fifth segment, this. Sixth segment, what should I do? I should be taking the largest value, but now this area will come with a negative sign, and then this. So the signed sum of areas of these rectangles will be an upper bound for the area that I'm looking for. And I can similarly find a lower bound by these green rectangles. So let's try to write down what I've done here somewhat more precisely. And so the basic thing that we are doing is we are subdividing the interval a to b into small segments. So I'll call that a partition of the interval AB. So let's write that down as a definition. Definition: a partition of the interval AB is just a sequence of points. So I'll call it P stands for the partition. What is the data associated with the partition? It's a sequence of points. The leftmost point has to be A. So I'll call that x naught. Then the next point is x1. The next point is x2 and so on. And this goes up to maybe a certain number of points. N points, well, n plus 1 technically. But the last point should be B. Right, so visually what I'm doing is I'm taking this interval A, B, and I'm choosing, so this A will be x0, and then I'm choosing some point x1, some other point x2 greater than x1, x3 greater than x2, x4, x5. So here's a partition with n equals 5. And now if I have this function whose area I'm interested in, whose integral I'm interested in computing, let me draw its graph. Then I can try to approximate this area, find upper and lower bounds as follows. So I want to find, say, an upper bound. Let's take this area region between x3 and x4. So here what I can do is I can get a lower bound as the area of this rectangle here, and I can get an upper bound as the area of this slightly larger rectangle here. Right, so I have a lower rectangle and an upper rectangle. What are the areas? So in this case, what I'm looking at is the area of the region here is, so this is some point xi minus xi minus 1. That's the size of the base. And the upper rectangle, its height, the outer rectangle, well in this case actually the upper rectangle, its height is supremum of f of x, where x belongs to xi, the closed interval xi and xi minus 1, or in other words x lies between xi minus 1. Xi minus 1 is the smaller one, right? So xi minus 1 less than or equal to x less than or equal to xi. So this gives me an upper bound for the area just between x3 and xi and xi minus 1 and xi. In this case, I is 4. So, and then I can just sum this over I. I goes from 1 to n. So this gives me an upper bound for the area under the curve. I'll call this UFP. And similarly, I can talk about LFP. I just replace supremum by infimum. And whatever this integral that we are trying to define, it should have the property that UFP is an upper bound for the integral and LFP is a lower bound. So before we can formalize this definition, let's just observe a few properties. So this is called the upper Riemann sum, or I'll just call it upper sum, and this is called the lower sum. The hope is that by partitioning the interval AB appropriately, maybe into smaller and smaller pieces, we'll get better and better approximations, better upper bounds, better lower bounds, and these upper and lower bounds will converge to let us compute the exact area. So, so let's just first investigate some basic properties of these upper sums and lower sums. So I have, suppose I have two partitions, then we'll say that a partition Q, let's say this Q is the partition A equals y0 less than y1 less than ym equals b. We say that it refines a partition P equals, as before, x0 less than x1 less than xn, which is equal to B, if the set x0 xn is a subset of the set y0 up to ym. So what we are saying is that we are subdividing each subinterval of P further into smaller intervals. And so in this picture, what I would do is, if I were to refine this, then I would be looking at something like, I might be introducing more points in between. So this would be, this of course y0 would be a, y1, y2, y3, y4, y5, y6, y7. Right? So you're taking each subinterval of P and dividing it further into smaller pieces. And the idea is that as you refine your partitions, you should get better and better approximations to the area under the curve. So let's try to formalize that. So I'll write that as a lemma. So let's have some notation for this. We'll say that P is contained in Q. Right? So the set corresponding to P is contained in the set corresponding to Q. We'll just write P is contained in Q. So the lemma says that if P is contained in Q, then the upper sum corresponding to UFP is greater than or equal to the upper sum corresponding to Q. So this upper bound gets tighter, and so does the lower bound. LFP is less than or equal to LFQ. So the lower bound is going up, the upper bound is coming down, and you're sort of squeezing the possible values for the area under the curve closer to the actual value. So I'll just sketch the proof of this. It's a very intuitive statement, and you should be able to write it down yourself, but let me just sketch the proof. So focus on one of the intervals. So suppose we look at focus on x I minus 1. So to xi. So let's just say focus on xi minus 1 to xi. So this xi minus 1 is equal to yj for some j, and xi, well, it's equal to yk for some k, and this k will actually be less than j. So what we have is this one interval between xi minus 1 and xi, and we have subdivided it into pieces. So this is yj, yj plus 1, and so on, and we go up to yk, which is xi. So the contribution of the interval xi minus 1 supremum of f of x, where x lies between xi minus 1 and xi, times xi minus 1. Now I can write this xi minus 1 as a telescoping sum. So this is equal to supremum f of x, xi minus 1 less than or equal to x less than or equal to xi, times summation L goes from, so if you look at this difference, xi minus 1, it's a sum of these smaller differences between the successive y's. So I can write this as L goes from j plus 1 all the way up to k, yl minus yl minus 1. Okay, now I can bring this supremum into the sum. So this is nothing but summation L goes from j plus 1 to k supremum f of x, xi minus 1 is less than or equal to x is less than or equal to xi times yl minus yl minus 1. But this is greater than or equal to, so this supremum I can reduce by making the set whose supremum is being taken smaller. So this supremum would certainly be less than or equal to the supremum of f of x, where x lies not between xi minus 1 and xi, but rather yl minus 1 and yl. See, this yl minus 1 to yl interval is one of these smaller intervals over here. It's much smaller than the interval xi minus 1 to xi. So this supremum had better be less than or equal to the supremum in the line above. And so this is summation L goes from j plus 1 to k yl minus yl minus 1. Okay, so we have this inequality for the block, for the contribution to the area that comes from the interval xi minus 1 to xi. So summing over all I, goes from 1 to n, what we get is, on the left hand side we'll just get u fp, right? It's just, this is just the contribution of the ith interval to UFP. And this is the contribution of the segments that lie between xi minus 1 and xi, that UFP is greater than or equal to UFQ. And this completes the proof of the lemma. Similarly, you can show that if Q refines P, then LFP is less than or equal to LFQ. So given two partitions P and Q, so let's say P is A equals x0 less than x1 less than xn is equal to B. Q is A equals y0 less than y1 less than ym, which is equal to B. And I'm not assuming that Q refines P or anything. I can talk about a new partition which refines both of them. Zk, where Zk is equal to B, where the set of points where you subdivide it, so where the set z0, z1, zk is just the union of x0, xn, y0, ym. Okay, then clearly P union Q refines P and P union Q also refines Q. We can use this to give an inequality between any upper sum and any lower sum. And so what we have is, for any partitions P and Q of the closed interval AB, we have UFP has to be greater than or equal to, well, it's obviously greater than or equal to LFP, but in fact it is greater than or equal to LFQ. The proof at this point is very simple. We know that UFP, well, that's greater than or equal to UFP union Q, because P union Q is a refinement of P. And that is certainly greater than or equal to LFP union Q, because you know UFP union Q is a sum involving supremums. This is LFP union Q is a sum involving infimums, term by term. These are in inequality. And then again, by the previous lemma, this is greater, P union Q is a refinement of Q, so we get that this is greater than or equal to LFQ. So we have all these upper sums and we have all these lower sums. Each upper sum is greater than each lower sum, not just the corresponding lower sum, but all the lower sums. So let's try now to get what is the best we can do with upper sums, what is the best we can do with lower sums. So the upper integral is defined as, so we can look at infimum of UFP, where P is a partition of the closed interval AB. This has to be greater than or equal to supremum of LFP, where P is a partition of AB. In fact, the first set is bounded below by any LFP, and the second set, any LFP, the set of all LFPs is bounded above by any UFP. And so the set has an infimum, the second set has a supremum, and the infimum of the set of upper sums is greater than or equal to the supremum of the set of lower sums. So we've squeezed the area that the integral that we want to define as somehow between the infimum and the supremum. And so what we say is, now we are ready to give the definition of the Riemann integral. So definition, let f from AB to R be a bounded function. We say that f is Riemann integrable on the closed interval AB if the infimum of upper sums is equal to the supremum of lower sums. Equivalently, no, let's not do that. This common value is called the definite integral of f between A and B, and it's denoted by the symbol integral a to b f of x dx.